Okay, today we're going to be looking more closely at semiconductors and how they are formed and how we use semiconductors to form a P and N junction and why they are important. So, let's look at the periodic table to begin with. So, here is group 4 of the periodic table, and we've got carbon, silicium, and germanium. So, semiconductors are usually elements from group 4 of the periodic table. Silicon, which is this one here, silicon's the 14th element, is the most common semiconductor. We grow silicon, I was going to SI for silicon, silicon crystals from a silicon ingot. And it's done in much the same way as you would if you've ever grown crystals in chemistry experiments. So you get a seed, but in this case the silicon ingot seed is massive compared to what you would just do, and it's in this kind of shape, and this is about 2 meters long, and this is used as the seed onto which silicon atoms will grow into its crystalline form. And then these are the crystals are then sliced to around about 1 millimeter thick, and then they are taken to be used in different electrical components. However, if we look at the chemical structure of silicon, now what does this mean if it's in the group 4? Group 4 means it's a valence. Group 4 means a valence of 4. So there's 4 empty spaces in the outer electron shell. Now let's look above. There's carbon, and we know carbon is in diamond form is the most strongly bonded substance that there is, and this is because it also has a valence of 4, and it will bond covalently with other carbon atoms to form this really strong crystalline structure, which is diamond. And so silicon will bond in a very similar way. So what happens is we've got the outer energy shell has 4 electrons in it, but it wants 8. To be full, it needs to have 8 electrons. So what happens is all these silicon atoms will share their outer electrons. So there's going to be 1, 2, 3, 4. These are the 4. I'm just drawing these little lines to represent the 4 electrons that are in the outer level of the silicon atom. So this one and this one here also has 4. So 1, 2, 3, 4. So this electron is going to share the position with that one, and this one is going to share the position of this one. Similarly, the outer energy, the outer electron from here will be shared with this silicon, and this silicon's electron will share with that one. And so what we end up getting is these really strong bonds, these covalent bonds. And this is exactly how diamond also is bonded. So you've got these double covalent bonds which are really, really strong. So pure silicon doesn't conduct. Because these electrons are going to be, the band gap between the valence level and the conduction band is going to be really high, because these electrons are now nicely bonded and they're not going to want to shift because of the strength of these covalent bonds. So what happens is, usually this can happen before they can take, you need to what we call dope the silicon. So doping means you remove a few silicon atoms, and it's something like 1 in a billion. It's not many. You remove a few silicon atoms and you replace it with either a group 3 or a group 4 element. Now you can do this by, before you've got your ignite, you can melt it down, put in some maybe gallium or some phosphorus, and then you can solidify it, form your ignite, and then grow your crystal. That's not a very precise way to do it. What tends to happen is you grow your pure silicon, so it's got this lovely pure crystalline structure. You slice it really thin, and then what you then do is you will dope those thin slices with whatever elements you want, and by doing it that way you can be very precise and you can engineer a semiconductor that will give you very specific properties. So we're going to look at this doping process in more detail. So when we add impurities, we're either going to be we're going to add two types. There's going to be two types, and that's either going to be acceptors or donors. Now I'm going to bring back up our periodic table so we can see this. So we've got our group 4, which we've got our silicon in group 4, and we've looked at our pure silicon structure. So silicon, oops, let me just get rid of that just now. So this form of silicon is called intrinsic silicon. Put it that way. So pure silicon is called intrinsic silicon. And we're going to then add either group 5 or group 3 elements to it. So by doing so, we're either going to remove electrons or add electrons. So group 5, group 5 elements, and examples of these would be normally phosphorus or arsenic is another common one. These act as donors. So these are going to give electrons, so group 5 are donors. So down here, there's your phosphorus, there's your arsenic. And group 3 elements, which is often boron, is one, there's boron up here, are acceptors. And so with an acceptor, we create holes. So let's look at what this looks like. So I'm going to actually get some colours up. Just give me a moment. There we go. So the yellow is going to be our silicon. Actually, I'm going to give this a bit more space. So our yellow is going to be our silicon. And now in this one, we have got a group 5 element. So either our phosphorus or our arsenic. And I'm going to put a 5 in here just to indicate this is a group 5. And so we've added an electron. So here's our silicon bonded with its double bond, sharing those electrons. And because it's a group 5 element, this can share silicon electrons, and it can share electrons, and the group 5 element can share electrons with the silicon. And this, just like we had if this was a silicon atom. But now, because it's a group 5 element, there's an extra valence electron, and it's just going to be here. So we've got an extra electron in the circle, in the structure, and we call this an N-doped silicon. So N-doped is group 5. We add an electron. Now the second type is P-type. So this is P-type. So again, we've got our electron, our silicons. But this time, we've got a group 3. So I'm going to put a 3 in here to indicate this is a group 3 element, like boron. Now because it's a group 3, it doesn't have 4 valence electrons, it only has 3 valence. Its valence is 3. So it only has 3 it's only got 3 it's only got 3 electrons to share. So it can share with this one. It can share with this one. Oh, that one can share with this one, sorry. It can share with this one. So it's that one is sharing, that one is sharing, and this one is sharing. And that's from the other silicon. But it doesn't have a valence electron to share with this silicon atom. So there is a hole, which we'll call H, and is a plus because it's that missing electron. So this has got a missing electron, and we call that a hole. Now, we keep this drawing up here because it will help us to understand what's happening. So a P and N junction is when a P-type and N-type silicon are interfaced together. So if you just had an N-type or just had a P-type, not much is going to happen. They're not going to do much. You need to take them and you need to put them together. And there's lots of different devices that have different types of semiconductor with different elements, different amounts. But one of the most widely used is a diode. So diodes are devices which are made of P and N semiconductors. And what are the purpose of a diode is a diode only allows electricity to flow in one direction. So we're going to look at this P and N diode more closely to see how it actually works. So this is our chemical. This is our symbol for a diode, and we've seen that before. And there's lots of different types of diodes. And we talked about how a diode can be used for changing AC current into DC current. We can also have a light emitting diode. Diodes are everywhere. Now, this is our little symbol, but what does it actually look like? So if we have, this is going to be an anode. So it's important to note the word anode means the positive terminal. And the positive terminal is connected to our P junction, our P-type semiconductor. And then we have our N semiconductor, and this is connected to a cathode. And again, remember the word cathode is negative because these words anode and cathode, they kind of just prop up all over the place when we're thinking about electricity. Now, let's look at this as what it would be like at a molecular level. So, Nrp, I'm going to draw this a line here, okay? Nrp Semiconductor, this is the one with the holes. I'm just going to draw holes. So we know that there's silicon. We know we've got this structure. I'm just drawing the holes. And then in here, in our N-type, we have these electrons going free. Now, where they meet, so this is our little boundary here. Now, this is the boundary. I want to get rid of the boundary. There's going to be holes here. And a minute. How's best to draw this? Here's our boundary. And we're going to have some holes. And we've got some electrons. But these electrons are going to fill up holes. They're going to move over and fill up the holes. And then what happens is, very quickly, you have the situation where you've got your P-type and you've got your N-type. And in the middle here, you've got these holes filled up with electrons. And then you're going to have these you're going to end up setting up a potential difference, an electric field. An electric field here. There's going to be an electric field. And there comes to a point where there's not going to have this migration. This migration here is called diffusion. So there's the diffusion of the electrons to fill up the holes until you have this electric field created, which therefore leads to a potential difference. And at that point, there's not the process of diffusion stops, and the electrons will not move unless you have an applied current where the voltage, the potential difference, is greater than this voltage here. And this voltage here is called the let's find the depletion voltage, VD. We call this bit here the depletion zone. So this is called the depletion zone. So let's think about this in terms of our energy bands. So if we have our p-type, actually I'm going to clear both of these. I can bring that back up if we need to talk about it. So we've got our p-type here. So I'm just going to write here that, just to remind us that the p-type is got holes. Okay? And then our n-type has the extra electrons. Just to help us remember, because the P and the N aren't very helpful symbols, to be my opinion. So here, if they're not connected, they're just separate, we have our, I'm just going to, for our conduction band, I'm just going to draw a line, and we're going to call it EC. So this is the energy of the conduction band. And then we have here the energy of our valence level. And we've got this gap. Now in our n-type, that's a bit less. So we have our EC and we have our EV, and they're lower than in the p-type. Now, what happens if when we connect, but we don't put a current through it? So we don't, when we put a current through the semiconductor, we call it applying a bias. So there's no bias. So this is just unconnected now. Now we're going to have no bias applied. So that means there's no current, it's not connected to current, it's just, we're just created that diode. So our energy band is going to be, our EC is here, and our EC for our n-type is down here. Actually, I'm going to make it a bit higher. I'll do it here. This is our EC. And what we now have is we've got a wee hill. And our EV is here. And our EV is a bit lower here. And we have this wee hill. Now, if we look here, and hopefully I've drawn it nicely, our conduction band here and our energy there's ability, you're going to have some electrons in the conduction band here that can move up into the conduction band here. They can move up that potential. But then what happens is they'll then stop. And you'll be left with that kind of level. Now, if we apply a forward bias, what happens? So that's when we're applying a voltage to drive a current through it. This gap becomes even less. The hill that the electrons have to go up becomes less than it did when there was no bias applied. Now if you put a current the opposite direction, so reverse bias that's called, you're going to have the opposite. You're going to have a much more increased bias hill to go up, and so it's going to be much harder for a current to flow when you've got the current going in the opposite direction. That's why a diode will only allow a current to flow in one direction. If you give it enough current, you can overcome this, but you'll probably break the device in the process. So the region where conduction and valence bands bend is the depletion zone, the depletion layer. And it's that place in our previous diagram where we had the electric field built up. Now I'm going to put a link to another video that I found in the comments, because the guy in that video has some really good animations that show how this works, and he has it all animated, and I think it makes it much more easier to see what's happening, because this is really quite complicated stuff. So I'll link that in so you can have a wee look. And if, yeah, have a wee look at that, and he explains with animation the process and how the current flows in much better detail. So I hope that helps.